Hello everyone. This video intends to present a very simple explanation of simple linear regression, and it is meant for budding data scientists and data analysts. So this presentation or this explanation will work in the following flow. First, we will cover the prerequisites to this explanation. So, what are the prerequisites? The basic mathematical concepts you should know to you should already know to absorb this small presentation well. Then, the prediction applications of linear regression in real life. What are the various domains in which linear regression is useful, or where it can be applied and it is being applied? Then how does it work? So a simple visualization to explain how linear regression can be used to predict a particular outcome in quantifiable terms. So then there is an introduction to the mathematics behind how linear regression works. Then we get dig a bit deeper into the mathematics, and we explain the concept of residuals and the concept of cost function. Then what are the assumptions for linear regression to work? And then finally, how a simple linear regression model is tested on how effective it is in making the predictions. So what are the prerequisites to understand this explanation really well? So basic maths, how a simple line, a linear, the equation of a line on a two-dimensional plane, on an x and y plane, which is represented as y is equal to mx plus c, or some other notation wherein y represents the independent variable which we need to predict. X is the y is the dependent variable which we need to predict. X is the independent variable who will which will take different values and will be used to predict y after coming up with this equation. This will be made simpler in the upcoming slides. For now, you just need to know that how this the equation of a line on a two-dimensional plane works. Then, how does how is the distance between various points on a two-dimensional plane calculated between using the Cartesian coordinates? So, for example, P and Q are 2 points on this particular x and y plane, where P is denoted by x1, y1, so x1 coordinate and y1 coordinate, and Q by x2, y2. And how the distance PQ can be calculated, or how QT can be calculated by simply y2 minus y1. This is the basic mathematical knowledge that you must carry. The third is in high school mathematics, if you could recall that maxima and so for any mathematical function which can be denoted using any shape or figure which can be denoted using a mathematical function, how are usually the maximum and minimum values of these functions calculated? So a function could have a variety of shapes, concave, convex. So that is a different thing altogether. But how the maximum and where on these graphs, where on these lines, where on these functions, the maximum and minimum values are usually found. So we differentiate. This is the technique where we differentiate that function and equate it to zero to find the conditions where the slope is zero. That is, this is flat. This is the slope, and this slope becomes zero here. So this is usually the point which is at the maximum or the minimum. And you should carry a small knowledge of hypothesis testing for testing significance of any variable. So to simplify hypothesis testing, that how would you check whether any value of any particular variable is statistically significant? So these are some real life applications of linear regression. So in all of these, if we won't go deep into them, but in all of these, usually one variable is calculated using known values of many other independent variables. So in the previous slide, we saw y is equal to mx plus c, and x is the independent variable. So there could be more than one variables which come under the multiple linear regression. We are just getting into this linear regression through a simple linear regression where the independent variable, where we have just one independent variable which is x. So it could be x1, x2, and so on. So for just taking one example of the tip, that for any automobile, if you want to calculate the average that it will give in certain conditions, so that is the variable we need to predict using some known variables from some known data. So for example, what is the speed at which a vehicle runs, what are the city conditions, the temperature of the surrounding temperature, and many other variables. We have data wherein we saw that under certain conditions, we saw that an automobile gives a certain average, and we have a database for that. So using those known conditions, we can predict that at particular given conditions x1, x2, x3, this will be the variable y, uh, which will be the average of the automobile. Simply for weather, similarly for weather data analysis, we are trying to predict whether it will rain or not, or what kind of precipitation we are expecting. We want to quantify that also. So we do that using existing data where multiple other variables which may affect the outcome of that one variable. We have that values. We have a complete data bank which we can use to predict a particular outcome. So similarly, market research studies astronomy, so finding weight of a planet using other data available. Financial domain, we can predict stock prices, knowing many other conditions more. There are a huge number of variables which can be used to do that. Then impact of environmental factors on ecosystems. So how the change in temperature or how the global warming affected a particular species or anything. So these are some real life applications, and which is this slide just intends to make linear regression a more interesting and not just a theoretical technique which is being explained. So, just trying to simplify this explanation, an independent variable, it could be one or multiple variables, put into a mathematical function which captures the relationships between between the independent variable and the outcome. So put it into a mathematical function can be used to predict a dependent variable. An example being a marketing budget, which could be among many other factors, one, two, three, four, which could affect a particular figure of sales. So how marketing budget can affect sales to very, this is an oversimplified explanation that just marketing budget data is there and now we need to predict the sales. There could be a multiple number of variables, which are the independent variables here. This is the independent variable. Sales is the dependent variable. So a graphical representation, this is how a linear relationship would look like. So increasing marketing budget. So for example, let the marketing budget, which is an independent variable, be on the x-axis. Increasing value of marketing budget is leading to increase in sales. This is a very simplified explanation. And just to after you see this graphically, and we try to capture this function, which would give us a model which can predict the dependent variable. And this model will be represented through a straight line formula, a straight line equation. And this is how the straight line equation looks like. And we will explain the error term in detail in a later part of the presentation, in the upcoming presentations. But this is how the linear regression model would look like, a simple linear regression model which will have just one independent variable x. It could be x1i and it could be x2i, x3i, and multiple other variables. Now, how linear regression? So now, what this slide intends to do is to explain how, to explain graphically or visually how linear regression comes to that best particular equation, which can be used to give the best, which would give the best prediction of a certain y variable. How do we do that? So we see, let these are the known data points, and we start with a simple line which has a slope of 0, where y is a constant value, this. So if we change the slope slightly in this graph, we see that the distances between these distances between the actual values, the observed values, and the line which we are trying to use to predict the values, these distances are maximum in there and they minimize a bit when we change the slope. So we have to reach a particular slope or particular beta 1 or particular m value, where we in the notation y is equal to mx plus c, m it is denoted by m, here it is denoted by beta 1. So we reach a beta 1 which gives us a line wherein these distances are the least. So this is the simplified explanation. Now we move into the mathematics part. How do we get this slope? How do we get these two parameters, mx plus c, that is beta 1 x, beta 1 is the m, beta naught is the c, the constant. How do we reach this, the values of, how do we find the values of these and get a particular single line which can be used to best predict the outcome, which can be used to best predict an a dependent variable. So the mathematical part, the three most important concepts to be covered in the mathematics of simple linear regression is the concept of residuals and a method called least squares method to fit a line to the data and value of r square. So this will be explained in the upcoming slides. So starting with the concept of residuals. In the previous slide, we saw that we reached an equation having a slope where these distances are minimized. And if these distances are minimized, the sum of these distances are minimized, this line will best describe the points, the scattered points, because they are showing a trend and this line would best cover that trend. So now what method is used to ensure that these distances are minimum? It is called the ordinary least squares method, wherein the squares of these distances is minimized. We need to find that minimum value of the sum of squares of these values, that minimum value which will give us the best line. So, which brings us to a concept or a terminology called cost function. Cost function in any mathematical model or any, say, machine learning model, cost function is that mathematical function which, when minimized, will give us the conditions where we will get the best fit line or the best fit mathematical model. So, right here in this case, in simple linear regression, RSS is the cost function, which is the residual sum of squares. So in previous slide, we saw that there was a line with, and our target was to minimize the sum of squares of distances of those scattered points from that line, which would give us the best fit line. So this is ordinary least squares method where we calculate these distances and we minimize these distances. And how do we do that? So in theory, there are two methods which can be used to minimize the cost function to get that ideal conditions which will best describe the scattered data on that graph. And one is the differentiation, which we also covered in the initial slide. We said that by differentiating and equating the slope of that line to zero at that point, slope of that function to zero at that point will give us the maximum or the minimum value. So this is one method to get that maximum or minimum value, and the other method is gradient descent, which is covered in the next presentation, which is out of the context of this particular presentation, because right now we are dealing with simple linear regression, and this is the method employed in calculation that in arriving at that best fit line, which describes that data best. So how do we differentiate? The residual sum of squares, RSS, is the cost function, and this cost function can be written as yi. This is the observed data. So it could be the scattered points, the scattered points, the actual observed values are denoted by yi, and beta naught plus beta 1 xi. This is the predicted value. This is the line. So the line will have that slope of beta 1 and that constant of beta naught, and xi will be the x value of that line. So when we calculate the difference between the observed and the point on that line, and we square that, and we sum of all those, and we calculate the sum of all those squares. Now this entire thing, if we minimize this entire thing, we will get that best line which is closest to the scattered data. So here is the method, which is the differentiation method. We take partial derivatives with respect to each coefficient, beta naught and beta 1, set them equal to 0. So in the initial slide, we saw that if we take derivatives, if we take partial derivatives, let's not get deep into that. Right now, we are just finding the derivative of y with respect to x, because these are the only two dimensions we are dealing with. These are the only two variables we are dealing with, one independent and one dependent. So when we differentiate that and equate it to 0, we will find those conditions, or we will find that beta naught and beta 1 value where that line will best describe those scattered points. And this is what the outcome of this method is. So after equating it to zero, we get these two values in that simple linear regression model, which will give us the ideal conditions or the ideal slope and constant of that line, or the ideal intercept of that line with the y-axis. So now, which brings us to the next part, that the third part of that mathematical understanding, the R square. So what is R square and why is it needed? So, for example, we have this equation. So, this equation has three variables and one error term. So, let's just look at these three variables for now. These three variables, or in our case, it was simply x1, and we ignored these two. But in real life, there are multiple variables. So, as we took example of that automobile performance, in that also there are multiple factors. In real life, there are so many other variables which are used to predict this y. So now these variables could have different units, could be measured in different units. So this could be, for example, temperature could be simply in degrees Celsius, and this could simply be the concentration or something related to the fuel being used. So, and this could be something else. So now these could have different units. Some values could be in millions, some value could be in just hundreds or tens. So this makes this, but when we calculate, when we are working on that cost function, we are differentiating this. Having such large differences in units of these coefficients, or the enormity or the volume or the size of these coefficients, would make working on this model tougher. So calculating this will become all the more mathematically difficult. So now, our target was to find that the minimum value of this, the summation of squares, we wanted to minimize this. So now, how do we say that the conditions, how to make it simpler? So R square comes to the rescue because it is calculated from 0 to 1. So otherwise, this value, the sum, this could be a huge value, which could be a part of some value in millions, then some in tens. And R square is simply a term which ranges from 0 to 1. It does not have to be in millions or tens or hundreds. And this will give us the efficacy of this model, or efficacy of that simple linear regression model that we are building, and that line that we are trying to arrive at. So this brings us to two new terms. When we have to understand R square, we need to understand two new terms. So RSS, this we are already aware of. How we are aware of? This is the line, this is the observed value. So this is the distance between observed value and the line, and we are trying to minimize the sum of squares of these residuals, which is the RSS, which is the cost function. So this we already know. Now, let's say this is the mean value of all the observed values, mean value of all the scattered points here. Let it be denoted by y bar. And this, we are introducing a new term, explained sum of squares. So the line we are trying to arrive at, the final fit line, will have distance from an average value. It could be a negative, it could be a positive distance, and this is called the explained sum of squares. And the sum of these two, so this portion where the difference between that line and the average value, and then the residual, if we total it, this is the total sum square. This is constituted by RSS and TSS. Now, since we are targeting to reduce this part, so this needs to be minimized. So this proportion out of this whole needs to be minimized, and this proportion out of this TSS needs to be maximized. And this is where R square comes into the picture. How? So R square is essentially this ESS part, explained sum of squares, by the total sum of squares. So we want this to be maximum. We want this part to be maximum and this part to be minimum. Since this proportion needs to be maximum, this should be as close as 1 to possible, or as close at 100% as possible. So this value, when it is 0.8, 0.9, 0.95, 0.99, the better it is. We have arrived at the best fit line when this R square is maximized, and it ranges from 0 to 2, because we are talking about proportions. We are not talking about absolute values. This is where R square is used to test the efficacy of a model, to understand how effective this line that we have arrived at is in predicting the value of y using the available data. So summarizing so far, this is a linear model represented by a simple y is equal to mx plus c, or beta naught plus beta 1 x. A line is fitted to the observations by minimizing the sum of squares, which is RSS, the cost function, by differentiating it by taking partial derivatives and getting the conditions where we get beta naught and beta 1, which will define that line for us. Linear regression LR gives one y for each x, but in reality there is a distribution of y. If you look at the scatter plots, there is a range of values of y on a particular x. Since now we are using this line to predict only one y, so there is an error that is likely to be there, and there's a distribution of error because this is a range of values. So error will also have a range of values, which will have a distribution. So which brings us to the assumptions for simple linear regression to work. So this is what we have learned so far. This is the scatter plot. This is the data that we are likely to have, where we can employ linear regression to get a predicted value of y, which is the target variable or the dependent variable. For all this to work, for we are applying this technique. Where we can apply this technique, there is a likely linear relationship between x and y. So we should have that sense from the data that when one variable, the known variable, is increasing, the other variable is also showing an increasing trend. So using that, we can, if we notice that, if we can get that intuition, if we can get that feeling, we can deploy this model. Error terms are normally distributed. This is required because we defined error just above, why there is a distribution of error terms. Now these errors need to be normally distributed so that we can make statistical predictions out of this model. Error terms need to be independent of each other. This essentially means that these error terms, if they are dependent on, say, there is a range of error terms. Let's say it's E1, E2, E3, E4. Now there is an error term E1. Now there's an error term E2. Now if E2 is dependent on E1, which is the previous error term, then it is not there. Then which means they are not independent of each other. One does not precede each other. The existence of E2 is not directly dependent on E1. There cannot be a dependency on each other. Otherwise, there is a redundancy in the entire model, because if E1 and E2 are dependent, then there are the other the variables due to which this error term is getting created are also dependent on each other, and these are not mutually independent variables that we are working with. Error terms have constant variance, so this distribution of error terms should have a constant variance, which is also known as homoscedasticity. So if the error terms, so if this distribution works in a way that error terms keep on increasing as we go ahead on x, so this will become a heteroscedastic model. And why heteroscedastic model will not work? Because then the error term will not remain independent of each other, because as the variables are increasing, the errors are also increasing, the independence is lost. So now we have arrived at the best fit line. So how to test the efficacy of this model? How to know that what we have arrived at, what we have calculated, is good enough? We do that because, so how did that line get defined? Beta naught and beta 1, and are these, so beta naught is the intercept or the constant term, but beta 1 is the slope of that line, and which will ultimately determine how good that line is, because that, when we saw in the initial slide that we were tilting the line bit by bit, and we arrived at a particular slope where that line best fitted the scattered data. So now, is that beta coefficient significant? Is it statistically significant? Why do we need to check it? Because simple linear regression is meant to give us a line, and it could give us a line to any scatter plot. But then, what is the use? So, for example, this is scatter plot. The observed values are all over the place. This is not showing a very specific, very definite, linear relationship. It does not show that. But still, if we apply this technique of simple linear regression, we will get a beta value. We will get a best fit line, because we will get a line which will say that the differences from the observed value, the sum of squares of residual, is least. But is it good enough then? If beta, If we check it for statistical significance and we find out it is not significant, then x and y are not very well related, which is the case here in this scatter plot. We can see that x and y are not very that well defined of having a linear relationship. So if we check beta 1 coefficient for statistical significance in this case, we will find out that it is not statistically significant. How do we do that? So we form a hypothesis. The null hypothesis, the no change hypothesis will say that beta 1 is 0, it is not statistically significant. And the alternate hypothesis will say it is not equal to 0, which means it has some significance. And so if we fail to reject the null hypothesis, if we fail to say that this is rejecting the null hypothesis. We reject the null hypothesis when we say that beta naught is not equal to 0. But if we are not able to say that, then beta 1 is close to 0 and it is not statistically significant, and then model is no good. And how it is done? It is done under a t distribution. So why not a z score is used and but a t distribution is used? That is for another presentation. But right now this is defined through a t distribution. So we calculate the t score for the mean point, which is assumed to be 0. As per null hypothesis, we had assumed that beta 1 is 0. So beta 1 is 0. So if you remember that the formula says x minus mu by standard error. So here the mean value is 0, so mu is 0. So x1 minus mu by standard error comes out to be beta 1 by standard error of beta 1. So this is the estimate of the slope coefficient and this is the standard error. After calculating the t value, we look up the corresponding p value from the table and compare that with the value or given value of beta. So this will be covered through a real example. And what other things we can test in to say that our model is good or not? We can use the error terms also. So in the assumptions, we had made some assumptions for the error terms. So we build a histogram of error terms. It should be more or less, it show some normality, and then we should check that we can plot these points and we should see that x and y are independent and there are not any specific patterns where there is a very direct relationship between x and y. So they should be roughly linearly dependent but not having an exact relationship, linear or otherwise. So these are the two things that we need to check. So significance testing, there is an example. So x these are the values that we calculated. Ultimately it came down to value of b1 from that formula that we had got in the other slide. By using that differentiation, equating it to 0, we got this value of beta 1, and this value of beta 1 is 1 in this case from this data. The standard error term is 0.297 and the t-score is calculated as 3.37. So now this 3.37, we checked it for a 95% confidence level. The degree of freedom is 3 because there are 5 variables and n minus 2 is 3. So we checked it and the value came out to be 3.182. Now since the t value calculated here is greater than 3.182, it is on the higher side, we can safely reject the null hypothesis and conclude that the slope beta 1 is significantly different from 0 at a 95% confidence level. So please note that this is not this is an example. This is not the was not our mission to reject it if we had taken these values, then definitely we would have had the model would be no good because we would have failed to reject the null hypothesis. In that case, the null hypothesis would have been true if the data for this graph was taken. But right now we have taken data from this which has a clear linear relationship. We can see that y is increasing when x is increasing. Since there is a clear linear relationship, we are seeing that the beta 1 or the b1 is significant in this case and the model is good. We are good to go. So this was a very basic explanation of simple linear regression. So upcoming presentations will cover it in more detail, and these are the things that will be covered. So in real life, there's a huge number of variables we have to work with, which comes under multiple linear regressions. And just like we had assumptions for simple linear regression to work, we will have some consideration for implementation of multiple linear regression. A concept of multicollinearity will be introduced. The how to deal with category